Modern coding agents operate through continuous execution. They spawn workers, track multiple objectives, and compact their own context over thousands of tokens. Traditional benchmarks measure a final pass-fail result. Did the patch fix the bug? But infrastructure has moved toward loop engineering. Systems now add a high-level control surface over the harness, requiring agents to manage persistence across an extended timeline. Grading only the terminal state obscures the development process. It makes it impossible to see if the agent actually maintained its internal logic or simply arrived at a viable artifact by chance. These benchmarks cannot track an agent's ability to route residual work or preserve its earlier progress as new requirements are added to the codebase. Using terminal outputs to grade loop-driven agents masks the specific failures that cause autonomous systems to collapse during long-horizon work. LoopsBench represents a software task as a dependency DAG. Every requirement is mapped as a node in a directed acyclic graph, defining the exact prerequisites for every line of code. Under this structure, a specific observation emerges. Even the most capable configurations, like Claude Opus 4.7, resolve only 25% of these tasks. These models possess significant raw code generation ability, yet they plateau at this quarter mark. The failures center on what the researchers call loop obligations, the requirement to maintain a persistent global plan and manage the regression pressure that builds as dependencies accumulate. Understanding why this ceiling exists requires a look at how LoopsBench deconstructs a coding task into its mathematical components. The benchmark is built on the development unit. Each node is a self-contained bundle consisting of a requirement, a file scope, a prerequisite set, a reference patch, and standard tests. These units are derived from source provenance. Their boundaries are defined by merged pull requests, released modules, or documented methodological increments. The connections between these units follow four patterns: pull request chains, structural reuse of a module, functional API calls, or compositional layering. Edges are admitted only through unambiguous evidence, such as symbol-level imports or overlapping edits. A list excludes hot monoliths or generated artifacts that would otherwise create false dependencies. This filtering prevents files like lock files or massive central headers from generating spurious chains that don't reflect the actual logic of the software. This graph is an evaluation contract. It measures the regime of incremental development, setting aside tasks requiring exploratory redesign. By grounding the DAG in strict provenance, LoopsBench creates an objective map of the obligations an agent must satisfy to reach completion. To score progress, the runtime identifies the ready frontier. This formula calculates which nodes are eligible for work. The frontier is restricted to nodes not yet completed. Crucially, a node only joins the frontier once all its prerequisites satisfy their own test requirements. Nodes with multiple predecessors act as checkpoints. Descendant tests remain deactivated until the checkpoint moves to a passing state. This mechanism governs scoring, not editing permissions. The agent is free to edit any file at any time. If the runtime blocked edits to downstream files, the agent could navigate the graph by simply waiting for the environment to grant permission. The agent is never told which unit is ready. It must deduce the prerequisite structure through its own analysis of the requirements and the test environment. Scoring against a frontier while allowing total freedom of movement reveals if an agent can plan a viable path or is simply making uncoordinated changes. Once a unit satisfies its requirements, its tests are classified as regression obligations. These tests never retire. They are enforced on every subsequent layer as the agent continues its work. If an agent edits a code generation unit but breaks the underlying parser, the parser test will fail on the new layer, regardless of whether the code gen unit itself passes. Crucially, the runtime provides no staged feedback. The agent is not told when it breaks a regression obligation. It must maintain its own internal model of the satisfied codebase. To manage this continuous testing, the benchmark utilizes a dual container snapshot pipeline. The agent edits in container A. The runtime takes snapshots of the workspace on a fixed cadence and ships the diffs to container B, where the referee runs the active test layer. This creates a queue of monotonic edit states. Metrics are calculated at real change points, providing a high-fidelity look at the loop's rhythm. This combination of regression pressure and snapshot scoring creates a comprehensive view of an agent's state discipline over long durations. The data from these runs shows a clear limit. The strongest configuration tested resolved exactly 25% of the tasks. Without an external continuation step, that success rate drops to approximately 17%. Testing different models under a fixed loop structure results in a similar performance plateau. Swapping loop architectures while holding the model constant produces the same result. The ceiling is persistent. Models can solve local issues, but as work accumulates, they struggle to maintain a global plan. Agents frequently fail to route residual work, often abandoning earlier obligations to focus on the immediate, local requirements of a new unit. These results suggest that scaling LLM parameters alone is insufficient for long-horizon software development. The bottleneck is the architecture of the loop managing those parameters. The planning and regression data reveals a structural trade-off. We can plot planning fidelity, how well the agent followed the DAG, against the rate of regression. Closed, tree-shaped loops like claude-code appear in the upper right. They show high fidelity to the prerequisite structure. However, they achieve this through over-parallelization. Spawning concurrent workers creates opportunities for regression, with independent workers breaking tests peers depend on. Open linear loops appear in the lower left. They have near zero regression, but largely fail to discover the task's prerequisite structure. By working strictly in sequence, these linear loops avoid breaking code, but they never resolve the complex dependencies required for full completion. Dynamic workflows and context renewal don't remove regression pressure. They move it to the handoff between workers. Even in this incremental development regime, every loop profile regresses. As agents build upward, they consistently erode their own foundations. LoopsBench provides a measurable baseline for long-horizon progress. Until an agent can manage its obligations across a dependency graph, the 25% ceiling remains the limit of autonomous software engineering.